sort of simpler designs, as far as like, putting it together and all that. Simple instrument it is not, because there's a lot of programming, of course, that goes into this as well. It's all programmed in Circuit Python to make it as accessible as possible while still being a higher level language, so that people still start to get an understanding of instrumentation language. Obviously, we can escalate that up to C and C++ and all that, but again, we wanted a nice entry point. So we're making these things hierarchical as terms of complexity and all that sort of stuff. And so what this is measuring is particulates, CO2, we got barometric pressure, relative humidity, all that fun stuff. We have what's called we called it AQI in terms of particulates over here, because true AQI uses a bunch of different measurements, and it's like a 24-hour period. So it's basically much more complex than this thing. But in terms of particulates, that's sort of the AQI that we're looking at here. And so, like I said, it's just fun to take it around to different places, because basically the measurements are going to vary from place to place. The closer I get to, say, the traffic, I anticipate at least that the more particulates are actually going to be present, because there's lots of particulates. People's car tires and all that kick up a bunch of stuff, including some pieces of the tire itself. And so you would see that. Now, obviously, you might not do that with, say, students or anything like that. You're getting too close to the traffic, but there's a bunch of other fun things. If you're doing it inside, we're, doing something we came up, and this is Paul's name for it, called measuring at the speed of smell. And that's basically using like buttered popcorn. You put it in the corner. You don't start microwaving it quite, the start. You have the students start recording down, the measurements they're seeing, the particulates, all that. And then you start it up, okay, with the buttered popcorn, and you see the particulates rise. Buttered popcorn, it really shoots it out. It's a lot of fun to cook, have these things near where you're cooking to see how, crazy the air gets. It's very, very interesting, basically, goes throughout the classroom. Now, of course, you can measure the classroom and all that sort of stuff and see, how well ventilated it is and all that sort of thing. So, bunch of fun stuff. Out here, again, we're getting pretty good air quality, 344 ppm. So we could breathe deep out here. I've done this, if you get a crowd of people, start rising and all that sort of stuff. We were just at South by Southwest, and we had a massive crush of people. We didn't anticipate that many people, but I was watching the CO2 levels just rise and rise and rise. I'm like, geez, man, this was a slide, and that was a gorgeous, huge area with vaulted ceilings and all that. Anyway, basically, this helps you become your own scientist. This car over here, going to be emitting, a lot of CO2, a lot of particulates and all that. I don't know, but this does have an SD card on here. And so even though that was a brief moment in time, it might not quite reflect on the screen here, which is, kind of harder to see if you don't have a nice little hood on there. Over in Goddard, people are coming up and breathing and just seeing if the CO2 is spucked. So it makes it, again, it makes you curious. It makes you want to explore. And that's what we're all about, exploration, right? Okay, so and that's just the AQ. And again, this is, one of the simpler designs as far as that's concerned. Okay. Now we'll move on to, and I'll show you the other two. So these guys are basically in the same vein as the AQ. Okay. So these are all done with connectors. They're all low costs. They're all designed to make things approachable. Okay. So for instance, this one right here is a spectrometer. It's 18 bands from 410 to 940. Has a lot of parallels with a bunch of different satellites up there like PACE and Landsat. And various other things. But again, it's all connectors. Now we've designed 3D cases and 3D housings for these things. This one in particular is actually a drone housing. You can put this on a nice little quadcopter because it doesn't weigh that much. Okay. But we also want to make sure that, basically that is accessible so that, again, anyone, hopefully anywhere on Earth, can start to have, access to an instrument, and start to try and understand what's going on around them. So when I use this guy, for instance, the spectrometer, I'm not measuring the sun's light and all that sort of stuff because that would burn out the sensors. That's not what this is one is for. It's meant for reflectance. Very simple, like 2-button design, power button, and a nice little green button here. And the green button, basically, I can cycle through the different wavelengths and see, you know, what the measurements on those wavelengths are. Its default screen has a nice graph here showing the visible and then goes into the near infrared. Okay, and I can take it around and take a look at the different spectra. Now this is a logarithmic scale. Okay, so right now I'm probably getting very low readings, but you know, and relatively, you know, flat because I'm looking at a dark surface. But let's take a look and see what it looks like over on a green surface. Right, you see a patch of grass over here. Okay, and I should say the swath on this thing is about a 1-to-1. So about the distance that I'm standing is about the sort of conical swath of the ground here. Now, if you come over and take a look at this screen, you're going to see that the visible is down, you know, it's higher near infrared than everything else. And again, this is a logarithmic scale, so the visible might actually be quite a bit higher. But, you know, vegetation and all that, you know, again, as green as like, you know, these leaves and all that are, and this grass is, it's actually reflecting near infrared about twice as much. Okay? And so we see that from space as well with like Landsat and PACE and all that, and they do, you know, different vegetation indices and all that. And in fact, well, the webinars that we just did, we go through and how to do like NDVI, which is Normalized Difference Vegetation Indice, which was developed by Compton Tucker over there, you know, using Landsat in the 70s. I think he's just got a big award for it. But we show them how to do NDVI, you know, basic NDVI with some of these instruments, and of course explaining to them what it is and all that. Or it's just a ratio between, you know, the near infrared reflectance and the red absorption. Okay. But with it, you get to tell, like, you know, properties about like plant health, density, productivity, all that sort of stuff. Okay. And so that's one of the things that we do. And when I'm inside and indoors, this thing actually has some lamps on here that will emit. That will be basically like, you know, replicating, you know, sunlight spectra, if you will. So I hold it down for about 3 seconds, and you'll see 2 lights on here. Maybe with the camera, you'll actually pick up some, and the third one, which is NIR, but you know, us human beings won't be able to see it. And then you can, because it's got a nice little baffle here, you can actually just flatten the leaf and you press it right on there. And again, you should see a big old spike in the near infrared. You should see some, you know, dips in the red and the blue, as well as a spike in the green and all that, you know, showing sort of the chlorophyll absorption rates and all that. And again, near infrared reflectance. Okay. And all that data is recorded on a CSV on this little SD card here. So if you can do all the fun math and spreadsheets that you want, same thing, of course, with the AQ. Now, we've talked about that. Let's go to heliophysics. Heliophysics, again, this one also, just like the other one, we actually have a printout, and you can put it on a piece of cardboard and just, you know, build your own heliophysics instrument, or we have this optional 3D printed case, which is really nice. This is also, again, all of this designed by Paul Morrell, creator and lead engineer. And so this little ball here, which is, you know, where everyone's focal point goes to, and they always want to push it, so you might actually see a little bit of smudging on here, is a diffuser. And what it does is sort of just evens out the light. Okay, and so it's got a spectrometer sensor under here where it's measuring the amount of light, you know, in the different spectra. And this is only 10 bands from 415 to 680. Okay, and so you do point this at the sun. So how much incoming solar radiation and all that. Okay, and then so if we're under canopy, it's going to change, obviously, right? Same thing with the UV. For indoors, you shouldn't get any UV at all. Okay, even behind a window. All right. Outdoors, you're going to have different, you know, things going on. So we have a bunch of clouds overhead. It's very overcast. Okay, so how is that affecting our light spectrum? And so I was using a combination of all of these, the AQ, the Helio, and the Q2, the spectrometer, basically. And, you know, if we had an enclosure and all that, we could measure not only the, you know, incoming, you know, say spectra from, you know, the grow lights and all that sort of stuff. We could measure, you know, the productivity of the plants, as well as another measure of the productivity would be the respiration of the plants themselves. So if we put it in enclosure, so if you want to encapsulate it all, you know, that's a nice little fun system that you could do. And I'm sure there's other examples as well. Okay, and so for PACE and all that, I actually was using one of these, and I had little petri dishes, and they have this awesome color wheel with like showing the different types of phytoplankton and all that based upon watercolor, you know, that it might be in there. So I would, you know, I'd make some of the petri dishes look sort of like, you know, so there's colors and all that, but you can just start to discern, you know, the different colors, of course, with this and all that. So pretty much, you know, again, this is a very versatile, useful tool. And one of the And why would I do that with all of these? Well, because, you know, seeing is believing. And I can tell people about Landsat data. I can tell people about PACE data. I can, you know, show them stuff up on the projector and all that. Well, once they can take their own measurements, see that, you know, that measurement in real time and that they took it, then you've, you know, any skepticism that they had about what these things are doing and why and all that sort of flies out the window. And literally this has happened time and time again where it's like 10 seconds and they're like, what else can you measure? And so you skip past the point where they're, you know, not understanding, you know, that particular thing. They're like, oh, it's measuring something and we can tell something about the Earth. And that's really one of the biggest things, because not a lot of people, I mean, you know, I take it for granted that I know that, you know, but a lot of people just don't understand these concepts. Okay. And really that's one of the basic concepts that we want to show. And then I'll put down like the Landsat benefits and, you know, thumb through. And I'm like, you know, what are you interested in measuring? What do you want to measure? What, you know, what's happening in your backyard? Is it red tide? Like, you know, the folks down in Sarasota, Florida that we're working with are doing? Or is it the farmer who had, you know, basically cheatgrass going over his wheat field? I do know that, you know, they were talking about like different like root rot in Idaho and all that sort of stuff with potatoes specifically. And there's like I think it was like red rot or white rot. There's multiple different types of stuff going on that are just affecting, you know, these different crops and all that sort of stuff. And are we taking a look at it? And, you know, again, because I'm biased and because I worked on Landsat for so long, I'm like, well, let's take a look and see, you know, if Landsat has anything to do with it. And lo and behold, 9 times out of 10, every time, you know, when I take a Landsat earth science type of niche or whatever, there's usually papers on it where people are actually looking at this stuff and trying to, you know, find out what is affecting this and how can we tell with these types of measurements. Okay. But that's where really where the bridge goes. This is bridging that gap between, you know, sort of understanding, say, like, you know, Landsat or PACE data or, you know, AeroNet and all that sort of stuff, so that, again, it brings it down to their hand so that they can really tell what's going on. This is the newest. We're still working on the software for this guy, but we're pretty solid on the hardware and all that sort of stuff. Okay, so we have base unit here, all right, and so this as a base is going to get sort of like it's got the capability of doing Wi-Fi, GPS, and various other things like that. Okay, and then we have modules. So the module that I just put on is the spectral module. Okay, and it's going to have a 18-band spectrometer, but it's also got surface temperature. Okay, which is something you do need to solder, and a LiDAR, a 4-meter LiDAR, so it's getting distance. Okay. And so the ultimate goal with this is we really want to try and do something with, say, evapotranspiration. So these are, you know, obviously Landsat inspired. So this is like a Landsat analog, you know, nowhere near the quality of Landsat. So don't get me mistaken on that. Okay. This gets you just sort of like, it's a step up to remote sensing is sort of what we're calling a step up to instrumentation, to understanding, you know, why we're looking at these things and, you know, making it more approachable and a little bit easier to digest that way. And again, we've seen this already happen where people are like, what can you compare this to, you know? And then of course, how good is this data is another thing. How good is this data? What is the need for this data? All of that. And this really starts to help answer those questions, you know? And it makes it affordable to do so. That's one of the biggest parts, is that it makes it affordable. And because these are off-the-shelf parts, you know, commercial off-the-shelf parts and all that, people are able to build around this. So if I go here, I am going to check the spectra here. Okay, so this is getting this conical view over here because the sensors are downward facing here. Okay, and you can see the bars here. So these are all bars across the wavelengths, and this is all at 20 nanometers full width half max. Okay, so that means basically the center, it's the measurements around the center, you know, the half of the measurement, the peaks basically, okay, of the measurements. Okay, and so you can see the nice spectra that it creates here. All right, and we get out into the near infrared in this chunk over here. So like I said, this one takes 18 bands and a nice conical view. And so you get to see sort of that nice flat plane with a few little dips and all that sort of stuff. It's also a logarithmic scale, so you got to keep that in mind as well. So when I get over the grass and all that, again, you should see a big spike in the near infrared and the green. Okay, and you're seeing big spikes in the near infrared. Okay, a little bit in that red edge over there too. And you see the green has a nice little spike there, but you see near infrared, it looks like around, was that like 860 or so, is really peaking over there. Okay. And of course, you got to think about the ground that you're looking at. And there might be shadows being cast as well. Okay. So there's, a bunch of different variables that go into doing, spectroscopy and all that. And so you have to be mindful of these types of things. So, yeah, so as you back off and all that, some of this, drops and some of it rises. Depends on what's going on. Now, there's not a ton of sunlight out here, at least that I could see, so there's not a ton of shadow, but you still are casting an obviously a shadow. Okay? So you want to make sure that you're, away from that so you can pull it out a bit. Okay? One of the other cool features, and this was an idea from Jesse Barber, we've been working with to do calibration on these things, is to put a cuvette on there. Okay, so let me get my materials here for some liquid spectroscopy. Okay, so you take like some distilled water, there's your control, and then you take, some stream water. I did a bit of snow. I did a snow out in the middle of my my yard, away from traffic and stuff, and then stuff right near the, all the turned up nastiness and all that. Okay, because I just wanted to see if there was a difference. Okay. Of course there was a difference. But yeah, so, and then also in talking about calibration, that's one of the other things that this helps you start to understand. So, me just going around and taking these measurements and all this is coming down, in as irradiance and all that. We need to calibrate it so that we can convert it to radiance and reflectance. Once we get it to reflectance, then we can start comparing it to some other, basically other devices, other instruments and all that. Okay. And how do we do that at a low cost? Because Spectraline costs thousands of dollars. All right. Now, I don't think I have a polystyrene sheet of foam with me at the moment. Okay. But we were using a few different weight references. Okay. So one of them would be a cutting board. Okay. And this was a brilliant idea that Dr. Petra Campbell had, our lead scientist for the team. She's like, hey, we, she was having a hard time keeping her polystyrene foam clean out in the Arctic, so she used the cutting board. Now this is a thinner cutting board, but basically you want to try and get a nice Lambertian surface to calculate it, to get your calibration against. And so when you do that, you should see a lot of these numbers and all that are sort of evening out. Okay, a lot of these wavelengths. Okay, now it is dipping a bit in the yellow and the blue, but you also got to think about what's happening up in the sky right now. So it's very overcast. So when you also have to take field notes. There's another thing. Okay, and so ideally you would go from calibration to your sample measurement and calibration. Go to the calibration sandwich. Okay, that's ideally how you do it. Okay, now, so we dipped into that, and so one of the cool parts about this, and this is Paul's brilliant idea, is that we have this base module here. Now we can swap it with a different module. And now it's an air quality instrument. And this one does all the same things that the AQ does. And I should mention that the AQ was developed with Dr. Nissa Rain and Paul Morell, okay, over like a weekend. And that was freaking awesome. And then the heliophysics was Pat Haas, Alana Resnick, myself, and Paul. And they were looking at the basically the STELLA 1.1 that we had, and they're like, "Well, what if we did this? What if we did this?" And then basically a helio instrument was birthed because Paul was just sitting there like, "Oh yeah, we could do this." He was building it basically on the fly, which is just fun and awesome. It's so much fun working with. Okay, so this one does all the particulates and AQ stuff. It also has a built-in methane sensor, so it's doing methane. So we just had a guy down in Pueblo, Mexico, Dr. Huichi Magaro Campos, that we've been working with. He's actually a plant physiologist, so he's doing principal component analyses using the Q2s. And his Q2s, his spectrometers were on rollers, when they were doing this stuff, and it's awesome. But he's also got like livestock and all that, so he's taking some measurements of, his livestock and all that sort of stuff, the methane that they're producing and so on and so forth. So this gives you, you got your barometric pressure, you have your temperature, altitude, humidity, your dew point, CO2, your methane, which is actually kind of spiking around. It is not. This is 83. This is usually down around 50. I'm wondering if it's because of the case or whether we have a problem. And then your particulates, and you get your particulate ratio, which is sort of the granule size. Okay, so particulates, we're thinking like, soot and smoke and all that sort of stuff. And of course, just all the other stuff floating around. Okay, so there's that. Last one here. At the moment, okay, because one of the ideas is to have this thing be, have a huge sort of like, basically off the shelf part, sort of like library of sensors. Okay, so now you can ask the question, what do you want to measure? And this is actually one of Paul's original things, is like, what do you want to measure, as being like just the first question on the website. So I kept that in mind, and when the new website comes up, you should be able to see the prototyping module. Now it's got a 5-volt bus, which we had to use for like the methane. It's got a 3-volt bus, which we had to use for like the surface temperature. Okay. And it's also got the quick connects, which we've used for some of these sensors and you've already seen before, all on this thing. But basically it leaves it open so that you can, basically use Velcro and put and try different sensors on there and all that sort of stuff. Obviously you would want to be like, well, what do you want to measure? Am I measuring sunlight? Well, then I might need this sensor, and this sensor. And then you can ask them, well, why did you choose these sensors? How good is data? All this fun stuff. Okay. And give them constraints and all that. But eventually, if they develop, a new prototype sensor and all that, they could develop a whole new casing for it as well. So then you have, again, additive manufacturing and instrument design manufacturing. Basically, there's a whole list of just different engineering aspects that this goes into. We've identified 14 so far, like optical engineering, and there's just tons and tons of fun engineering and all this different stuff. Even the joints themselves, these things, because we're working with PLA, and as Paul puts it, is very brittle and all that, and crystallizes pretty fast and is kind of tricky to work with. But all of these, like, these little, I believe they're called flexor joints, and he can correct me if someone else can if I'm wrong. But if you bend them too far, they'll break. But so you can see it snaps in. But if you have like a little, and again, I'm probably mislabeling this, but basically sort of a barrier, a wall here and all that, it keeps it from bending far enough to the point where it will break, so you can reuse it. Okay. And I mean, the engineering in this is just unreal. And then so you also have a little, your SD card in here. So it's taking all of these different measurements. Okay. Again, we've had these on drones. People want to put them underwater. We have a few different things that, people want to do different types of instruments and all that. So we've been working with folks. And again, right now it's a pretty small team. So we're really, we're trying to do what we can with what we have. So we're, doing a lot of like outreach and all that. Should say one of the most brilliant things that happened was Chris and I, the Lancet 8 and 9 scientists, basically said, we want to send out a bunch of these as boners. Okay. So, and it wasn't the 1.2s, it was actually the 1.1s. So we had 2 high school juniors, and they built 40 of these over a 10-week period. Not only did they build 40 of these, but they took a round of basically 2 measurements with each instrument that they built, okay, during that period. And they got done in 8 weeks. They beat it by 2 weeks. They were some of the best interns like ever. And so we sent these out across the country, okay? And I'm talking Alaska to Florida to American Samoa to Puerto Rico, all over the place, okay? And basically to teachers and those folks to come up with, like curricula and activities and all that sort of stuff. We're finding it takes about like eight months or so to really, because they just need time to do it with their students, to mess around with it, and then write it all up and all that. But it was a brilliant idea, and it really got us a lot of exposure. So it was a fantastic idea. And I should say also, as far as like the origins of this came along, this was spawned off of Intro to Remote Sensing 101 activity put together by Ginger Butcher. Okay. And then they discontinued the spectrometers we were using for that particular thing. Okay. And those were nowhere near the quality of these guys. But basically, so it's like, hey, we got, scientists, we got engineers. Let's see if we can develop our own. Eventually, we were put in touch with Paul Morell. Okay, he was already developing something somewhat similar. There are a few constraints here and there and all that sort of stuff, but he came up with the STELLA 1.0. Okay, and Ginger basically said, "Hey, Mike, I don't have the bandwidth for this really, so take and run with it." And take and run with it, I did. Okay, and it's spawned just tons and tons of stuff. It's fantastic projects, and a lot of people want these things because they're, like I said, it's very easy to start to relate as to why you want to take these measurements. Why do you want to have why do you need a pace? Why do you need a Landsat? And all these sorts of things, because they'll start to understand, oh, well, this is not the highest quality data ever. We want what's higher. And you got NASA, who's like at the tip of the spear as far as, calibration, validation, research, science, engineering, all of that. Okay. And what I say with these guys is we want them to be able to just grasp that spear, get on to the handle of that spear. Okay. Because we want them to understand, hey, we need to keep pushing the boundaries. We need a Landsat next. We need, the next, pace, the next, the iterations of these satellites, and continue pushing the boundaries as to, getting the best data, the best quality data more. And right now, Landsat is the best quality, spectral Earth observing data from satellite we can get. Okay. And so Landsat is supposed to be basically as transformative as ERTS, which was Landsat 1. So we want people to understand what the need is for this, and that's again one of the impetus for the Stellas, as well as, of course, understanding more about the instrumentation. So step up the instrumentation, step up to remote sensing, and what do you want to measure? That's sort of like encapsulating thing.